Okay, so those two things belong to the MPC paradigm just presented by Thibault. So we have a one-way function, basically, or a hard problem, where we have a secret X, which is mapped to a public value Y. And so we'll first design an MPC protocol that should verify that the sharing of X corresponds to the public value Y. Then using the MPC SDitH transform, we turn that into a zero-knowledge proof. And using the Fiat-Shamir transform, we can turn that into a signature scheme. So in this talk, I will mostly focus on the first step, which is how to design a multi-party computation protocol to verify some instance. And I will focus on two hard problems, which is MQ, the MQ problem, and the syndrome decoding problem. So here is the roadmap of my talk. So I will first give a bit of technical background, then we'll see the MPC protocols underlying MQOM and SDitH. Then I will present another MPC SDitH technique based on a threshold secret sharing. And then I will give the results that we obtained for the MQOM signature scheme and the SDitH signature scheme. Okay, so let's start with the technical background. So first, I'll recall the MPC model. So in this model, the parties receive a sharing of the secret X, and they jointly compute a function G, which should output accept if X is the correct pre-image of the output Y, of the public output Y, and reject otherwise. And we're in the broadcast model, as presented by Thibault. So in this model, the party basically will locally compute under shares and reveal some of the computed shares. So those, we say that those shares are broadcast, and we denote them alpha here. And when the shares are broadcasted, we can recompute the associated value alpha publicly. And this value can be used in the subsequent steps of the MPC protocol. We also consider some protocols where this function G might actually be probabilistic. So it means that we can have some false positives. So sometimes the function G will output accept, whereas X is not a valid witness. Okay, so this occurs with some probability that is called the false positive probabilities. In addition to locally compute on the shares and broadcasting, the parties can also request some oracles. So we have two types of oracle, a randomness oracle. So the randomness oracle will basically generate some random value and publish it so that it is accessible to all the parties. And we have a hint oracle that will distribute some sharing of a value beta. And this value can be, so beta is a function of the secret input X and the former random values that have been generated by the randomness oracle. So when we apply the MPC SDitH transformation, the randomness oracle is basically played by the verifier. So a random value epsilon here is a random challenge from the verifier. And a hint sharing beta is a sharing that will be computed by the prover somewhere in the middle of the protocol, and that will be committed by the prover for the next steps of the protocol. Okay, so in the MPC protocol that I will present, I will use polynomial interpolation. So this is very basic, but it's just to like fix the notation here. So I will consider some fixed points of a field denoted Fi. So let's say we have m such points. And if we have a vector of size m on the field, we can apply the interpolation of of x to derive a polynomial denoted large x here. And so this polynomial basically satisfies that when evaluated on f1, we recover the first coordinate of the vector, and so on until when evaluated on fm, we recover the last coordinate of the vector. So this is basic Lagrange interpolation. And this way we obtain a polynomial which has degree m-1. I will also use the Schwartz-Zippel lemma in its simple version. So basically, this lemma says that if we want to check the equality between two polynomials P and Q, we can simply check that they are equal on a random point. And so if we have a random point R, we have a probability. So if the two polynomials are not equal, the probability that, so that would be the false positive probability, basically, that P of R equals Q of R. This is upper bounded by the degree of the polynomials divided by the size of the field. And to see this, we have that P of R equals Q of R if and only if R is among the roots of P minus Q. If P is different of Q, P minus Q is a non-zero polynomial of degree D. So the probability to have this is the probability that R is taken among the roots of this polynomial P minus Q. Okay, so now I'll present the MQOM MPC protocol. So this protocol validates, verify an instance of an MQ problem. So we'll first define this problem. So we have three parameters. So a field FQ, a number of variables denoted n, and a number of equations denoted n. And when we generate a random instance of this problem, we basically generate a random quadratic system with m equation into n variables. So we will first generate randomly the solution of the system, denoted x. So it's a vector of n values. Then for each equation, we generate a random matrix. So this is the quadratic part of the system. And we generate a random vector, which is the linear part of the system. And then the system is defined this way. So we have, from the secret solution and the matrices and the vector, we derive the output. So this is a vector denoted y. And then the problem is from all the matrices, vectors, and the output y, one should recover the secret solution x. Okay, so the MQOM MPC protocol basically verify a solution to this problem. So the parties receive a sharing of the secret solution x, and they receive the MQ equations, so the matrices AI, the vectors BI's, and the output y. And they aim to gently compute the function g, which output accept if all the equations, if x is a solution of all the equations, and reject otherwise. Okay, so we have a two-step protocol. So in the first step, we'll batch the MQ equation. So so here we write an equation. Here we put all the terms on the same side, and we have to verify that the equation equals to 0. So we denote that EI of x. And so we have to verify that EI of x equals 0 for all the index I, for all the m equations. And so so the parties will ask the randomness oracle to produce some random gamma i's. And so those randoms belong to an extension of the field. And then we'll compute a batch equation, which is simply the linear combination with coefficient gamma I of all the equation EI's. And we will verify that this batch equation equals 0. So of course, if all the equations well equal 0, then we have that this batch equation equals 0. But we might have some false positive probability. Even if some of the equations are different from 0, we might obtain a 0 here. This is over the randomness of the gamma i's, and it occurs with a false positive probability, which is of 1 over the size of the extension field, so 1 over q to the eta. So this batch equation can be rewritten as inner product. So here we have we define some vector w this way and some value z this way. And actually, this batch equation is equivalent to this inner product relation. So basically, this inner product between x and w is it contains all the terms which are quadratic in the batch equation, and the z contains the constant and linear terms. And the nice feature here is that z and w are both linear or affine function of x. So it means that we can derive a sharing of w and a sharing of z locally, so the parties can locally derive those sharings from a sharing of the sharing of X. So that's the first step. We'll get some randomness from the randomness oracle. We compute this batch equation and derive the sharing, the associated sharing of W and Z. And then the second step is to verify that the three sharings of X, W, and Z indeed satisfy the inner product relation. So for this, we will locally interpolate some polynomials. So we will split the vector X and W into blocks. So we have N2 blocks. Each block is of N1 coordinates. And for each block, we will interpolate one polynomial. And then we can rewrite this inner product relation in terms of those polynomials. So we have a double sum here. We have a sum of the xj times wj and a sum for all the evaluations, so for the N1 coordinates in the evaluation points. And so we have to check that the polynomials that we have interpolated satisfy this relation. And this is equivalent to verifying the inner product relation. Okay, so for this, we will call the hint oracle to generate a sharing of the polynomial Q0, which satisfies this. So Q0 is defined as the sum of the product of the polynomial block by block, so xj times wj. And so if we will get the parties will get a sharing presumably of this polynomial, and then they will check that the sharing from the int is indeed satisfy this relation, this first point, and then they will also check that it satisfies this second point, namely if we sum Q0 over the evaluation point, we recover Z. So if we check those 2 points, we have checked this equation, which is equivalent to the inner product relation. Okay, so for the first point, we will actually rely on the Schwarzschild lemma. So we'll ask the randomness oracle to generate a random point on the field. Then we'll locally compute the evaluation of the wj polynomials on this point. So we denote that alpha j. So this can be done locally. So polynomial evaluation is linear. Then we broadcast those evaluations and recompute them publicly. So we have the evaluation of the polynomial wj on R. And then we can compute this sum of alpha j times the evaluation of polynomial xj evaluated in R. So this sum is supposed to equal the hint polynomial evaluated in R. So we compute the difference between those two, and if the hint was correct, we are supposed to get a sharing of 0 here. So this sharing is broadcasted, publicly computed, and then the parties check that this value equals 0. Okay, so thanks to the Schwarzschild lemma, this gives a false positive probability, which is about 2n1 divided by q to the eta. So I took a shortcut here. Actually, we cannot publicly recompute the alpha j because it leaks some information on W, which leaks some information on X. So in practice, we have to mask this value by masking the polynomial wj. I won't go into details here. Then to check the second point, we simply locally evaluate the hint polynomial on the evaluation point. So this is supposed to be equal to Z, and we compute the difference with the Z sharing. So here, once again, we are supposed to get a sharing of 0. So this is broadcasted, publicly recomputed, and then check for that the value v2 equals 0. Okay, so this is actually a simplified version of the protocol. We can save communication by removing the constant term of Q0 from the hint. So this gives a slightly more complicated protocol where we also kind of merge the two check and have a single value v, which is broadcasted and supposed to equal 0. But here you have the big picture of the MQOM protocol. Okay, so now I'll present the SDitH MPC protocol. So the goal is to verify an instance of the syndrome decoding problem. So this problem is defined by those parameters. So we have a base field FQ. Then we have a code length denoted M. We have a code dimension denoted K, which is smaller than M. And we have the weight of the solution, which is denoted W. And to generate an instance, we first generate a random parity check matrix H, which is of dimension M minus K times M. We generate randomly the SD solution, so which is a vector X with M coordinates of weight at most W. So it means that we have at most W non-zero coordinates. And then we compute the so-called syndrome Y, which is H times X. And so the problem is from H and Y to recover the solution X. So without loss of generality, we can assume that H is in a standard form. So it means that the matrix H, so the right part of the matrix is the identity matrix. And this enables us to write Y as this. So we have H prime XA plus XB, where XA are the K first coordinates of X, and XB are the M minus K last coordinate of X. And so this implies that we can consider that XA is the secret here, because XB can be recovered from XA and the public information from the instance. So basically, we have XB equals to Y minus H prime XA. And so this actually enables to reduce the communication cost. Okay, so to verify a SD solution, we will define some polynomial constraints. So we'll first interpolate the vector X. So remember that X has only a few non-zero coordinates, W of them. And so here the non-zero coordinates are represented by the dark gray, and the other are zero coordinates. So we interpolate the polynomial S. Then we define a polynomial Q, which is the product of X minus Fi for I belonging to a set E. And this set is defined as the indices such that Xi is different from 0. Okay, so if we look at the evaluation of Q in the evaluation points, we will have some zeros where we have non-zero coordinates of X. So those two vectors are kind of complementary. And so with this definition, this set E is at most of cardinal at most W, and then the degree of Q is of cardinal at most W. So with this definition, we have that the product between S and Q will evaluate to 0 in all the evaluation points. And this further implies that this product can be rewritten as a different product, a product between a polynomial F, which is publicly known and which is the product of X minus Fi for all the evaluation points. So this is sometimes called the vanishing polynomial over this set of points. So it's this polynomial F times some other polynomial P, which is of degree W minus 1. And so to prove that the solution X has a weight at most W, we can simply, so what we will do is to show that there exists a polynomial Q, so that the interpolated polynomial S times the polynomial Q equals this F times another polynomial. So the protocol will work this way. So the witness received by the party will be the sharing of XA, the secret part of X, and the polynomials P and Q, and also, of course, the public instance of the SD problem. And the function G that will be jointly computed by the party can be written this way. So it will output accept if SQ equals FP, where S is the polynomial interpolated from XA, XB, and where XB is recovered from XA. So here, this kind of encode the linear part of the problem, the equation Y equals H times X, and the weight constraint is checked with this equality. Okay, so for this, once again, we will rely on the Schwarzschild lemma. So we will check this equality on T random points. So this time we use several random points to increase to decrease the false positive probability. So the protocol goes as follows. So first we locally compute the sharing of XB from the sharing of XA. So this is linear. Then we locally compute the polynomial S by Lagrange interpolation of the sharing X. Then the parties will call the randomness oracle to get the random points to test the equality. They will locally compute the evaluation of the polynomials, the shared polynomials on those points. And then they will use a product check protocol to check that the product of the evaluations indeed equals, so the product of S applied to Ri times Q applied to Ri. In this equal F applies to Ri times P equals to Ri. Okay, so this is just a product here. So we have two sharing for which we must test the product, because here we have directly the product because F is public, so it's just kind of scalar multiplication. Okay, so for checking this product, we use the BN20 protocol, which I won't recall here. This protocol also needs randomness from the oracle, and it also has a false positive probability. So in the end, we obtain this a bit ugly false positive probability, but we have that it is exponentially small with the number with T the number of points which are used, and with eta the field extension. So we have different trade-offs. So I don't mention here, but actually we have a trick to avoid the interpolation at this step, which just slightly change the original witness, but I won't go into those details. Okay, so now I'll present the threshold MPC in the head approach. So this is an approach that we have proposed with Thibaut in a paper that will appear at AsiaCrypt this year. And so the principle is to use, instead of an additive sharing, to use a threshold linear secret sharing. So concretely, L+1 n threshold linear secret sharing. So such a sharing has those properties. So it is linear, so it means that we can still compute locally linear function. Then from any set of L shares, we have that any set of L shares is random and independent of the secret value X. But then any set of L+1 shares unable to reconstruct all the shares and to reveal the secret value X. And a famous example is the Shamir secret sharing, which is the one that we use in practice. So in this setting, in order to ensure the zero-knowledge property, we won't reveal n-1 party anymore. We will only reveal L parties, because otherwise we would reveal the secret. So that's an important difference. Also, another point is that in practice, we'll use a low threshold scheme for which L is small. So it means that we don't have a lot of randomness in the sharing, but we have a lot of redundancy. Okay, so let's see the differences in the zero-knowledge proofs obtained through the MPC in the head transformation. So in the first step, we generate and commit the shares. So here we won't use seed trees anymore, but we use, because we have a lot of redundancy in the sharing, so we'll use a Merkle tree. So we'll generate the sharing and then commit it with a Merkle tree. So each leaf will be a secret share, and the root will be the common commitment for the sharing. So it also implies that when we reveal some parties, we will reveal the share and reveal the authentication path to the Merkle root. Then another difference is that since we have redundancy in the sharings, we don't need to send the full sharing when we send a broadcast sharing. We only need to send L+1 shares because that fully determines the sharing. And so it implies that we only need to perform L+1 party computations. So because the L+1 party computations will define all the party computation. Then the verifier asks to open L parties. And that also means that the verifier will only verify L parties. So we have L+1 party computation on the prover side and L party computation on the verifier side. And this way we obtain a soundness which is close to the soundness that we obtain in the standard case of additive sharing. I'll try to give the intuition just after of how we obtain this soundness. But it's still a bit degraded. So we have 1/n plus p times something. So this something in the standard approach is close to 1. And here it's closer to n/2. So this is the specific case of L equals to 1. So it means that if we have an important false positive probability, then we have a stronger degradation of the soundness. So the threshold will be more interesting for contexts where we have a very small false positive probability. Then in terms of computation, we have here a constant number of computation of party computation. So 2 on the prover side and 1 on the verifier side against log n plus 1 and log n with the hypercube technique. But this comes at the cost of a slightly increased communication. So actually the communication is similar in both approaches, unless for the seed tree versus Merkle tree. So a sibling path basically reveals some seeds of size lambda, while an authentication path in a Merkle tree reveals some digest of size 2 lambda. So the size is just doubled here. So for instance, at 128 bit of security, the seed tree represents about 2 kilobytes, and the Merkle tree represents about 4 kilobytes. Okay, I think I'm short in time, so I'll just give a quick hint of the soundness. So here we have the n parties receiving their shares and computing some broadcast messages. So for now, I just assume that the false positive probability is 0. And then there is the message that is actually broadcasted by the prover. And we say that the party is honest if it matches, and the party is dishonest if it doesn't match. So in case we have L+1 or more honest parties, we can actually show that we are in the presence of a honest prover that knows a valid witness. So if we are in the presence of a malicious prover, the number of honest parties must be at most L. So in case it's strictly lower than M, the cheat will always be detected because we will open one dishonest party. So this cannot work as a strategy for a malicious prover. So the only strategy that can work for the malicious prover is to have exactly L honest party. And this won't be detected if the set of open parties match to the L open to the L honest parties. But if it doesn't match, this will be detected. So we'll have a soundness error, which is basically 1 over L among n. And so for L equals 1, we recover 1 over n. Okay, so when we don't have a 0 false positive probability, the analysis is more complex. So in the paper, we show that we have this soundness error, where here we have this factor that is more important than in the additive case. And we have also a more important degradation when we switch to the non-iterative setting when we apply Fiat-Shamir. So it's really important for the threshold case that we have a very small false positive probability. Okay, now I'll present the result for the MQOM signature scheme. So this is a submission by Thibaut and myself, which is based on the MPC protocol for MQ that I presented earlier. So it is based on previous work and propose some improved way of validating the MQ instance. So for the choice of the parameters, so for the MQ parameters, we took a number of equations that is equal to the number of variables. And we tested several fields. And for each tested field, we defined the number of equation and variables to satisfy a target security level, and for that we use the MQ estimator. Then for the MPC parameters, we took 256 for the number of parties, so that gave a good trade-off in practice. Then we tested several possibilities for the field extension eta and the split into blocks N1 and 2. And for each tested parameters, we derived the number of parallel execution that are necessary to thwart the generic forgery attack, basically an adaptation of the KZ20 attack. So this table gives the best parameter and size that we obtained for the first security level. And we choose to keep Q equals to 31 because it gives the shortest signatures, and it was also already considered in MQDSS, a submission to the first NIST post-quantum process. So this might have motivated some cryptanalytic attempts. And we also choose to keep Q equals to 251, which is a large prime field for which elements can hold in bytes, and which might be more amenable to the threshold MPC in the head setting. So for now, we didn't apply this setting to MQOM because it wouldn't give really good result because of the false positive probability, basically. And for all the instances, we also provide fast variants with a smaller number of parties, so basically 32 parties. So here is the obtained performances. So in terms of signature sizes, for the first category, we are between 6.3 and 7.8. For the other categories, between 14 and 17 and 24 and 30. And for the timings, we are from 1 to few dozen megacycles. So we believe that this could be optimized further, in particular for the arithmetic. And for the key sizes, it's pretty small. The key sizes are about a dozen bytes, always smaller than 200 bytes for all the categories. So in terms of comparison, so up to our knowledge, this gives the shortest signatures for non-structured MQ problem. There are other MQ signature schemes submitted to the new call of the NIST, which are either based on larger, so which have larger public keys, large public keys, so that's the case of UOV, for instance, or which are based on more recent structured assumptions, which is the case of Matthieu. And compared to other MPC in the head schemes, so MPC in the head schemes have between 5 and 10 kilobyte signatures for the first security level. So we see that we are not the best, but in the low range, range of this low side of this range, and that's what we can obtain for the MQ non-structural MQ program. Okay, so now I'll present the syndrome decoding in the head scheme. So this is a submission in collaboration with different collaborators listed here, based on some previous work presented at Crypto 2022. And so we have two variants, one named Hypercube, which is based on additive sharing with seed trees and the Hypercube technique, and a variant Threshold, which is based on the Threshold technique that I presented earlier. And so we considered two fields about the same size, which is the size that give good size for the signature. We choose to consider a binary and a prime field. This might be different in terms of cryptanalysis. We'll see. And the other difference is that the prime field has better arithmetic and platform in the absence of carry-less multiplier, while the binary field is better for pseudo-random sampling, which is used a lot in the Hypercube variant, basically. So for the other SD schemes, SD parameters, we choose them, so we kind of exhaust the possible parameters to resist to the known attacks, and in particular the information set decoding and the generalized birthday algorithms. And then for the MPC parameter, we also choose n equal to 256 for the hypercube variance. And we choose n equal to q. So that's something I didn't mention, but a limitation of the threshold approach is that the number of parties is at most the size of the field. And we use a threshold L equal to 3. So that gives a good trade-off between signature size and timings. For the field extension, we choose common field extensions for all the variants so that we have a single implementation of the extension field arithmetic. And then we try different values of t, the number of points, and obtain the tau, the number of parallel executions, to target for the target security level. Yeah, and basically choose keep the parameters that would give the smaller signatures. So what we obtain in terms of sizes, so for the hypercube, for the first security level, we have 8.2 kilobyte signatures, while for the threshold, 10.4. So we see that hypercube is 2 kilobytes shorter. This gap increases with the security category. We also have small keys, as for MQOM and other MPC in the head schemes. Then for the timings, so we have about 5 milliseconds to sign for hypercube and to verify as well for the first security level. While for threshold, we are faster, so 1.7 for signing. So this is between 2 and 3 times faster over the different security categories. While for verification, it's really faster, so it's 0.2 milliseconds, which is about 20 times faster for all the different security categories. Okay, and just to compare with other schemes, so to the best of our knowledge, this gives the shorter signatures for syndrome decoding on random linear codes. This is actually the only submission to NIST using the threshold MPC in the head approach. So this gives MPC in the head scheme with a fast variant, especially for verification. And compared to the other schemes based on MPC in the head, we are in the high range of the signature size. But yeah, that's what we can obtain for the SD problem, which can be argued to be a pretty conservative problem.